Hi, this is Adam Griffin with the second video for this week. So this is going to be problem number 3. And this problem deals with the relationship between frequency for a string and its length, the tension in the string, and the linear density. So question 3 goes like this. In a perfect fifth, the two notes have a ratio of 3 to 2. For example, 440 hertz for an A and 660 hertz for an E. Two strings, one of length 0.3 meters and the other of length 0.2 meters, are made of a material with a linear density of 0.005 kilograms per meter. So part A asks, what should the tension in the two strings be to give the fundamental or the first harmonic frequency of exactly 440 hertz and 660 hertz? So if we pay attention up here, we can assume, because it should go without saying, that if you have two strings made of the same thing, both with the same linear density, that a shorter string will produce a higher frequency. Just like if you were walking on a tightrope or something, which is super long, and you were to strum that, it would probably be too low of a frequency to even hear. So we know that the longer string is related to the lower frequency, so note A, and the shorter string is really related to the higher frequency. So what should the tension in the two strings be to give the fundamental frequencies of exactly 440 and 660 hertz? So down here I drew both strings. So this one is 0.3 meters, and when it vibrates it produces a frequency of 440. And then for the 0.2 meter one, it does 660 hertz. And then for both, the linear density is 0.005 kilograms per meter. So the relationship between frequency, length, linear density, and tension is this equation. So this is the first harmonic frequency. And we know that that's 440 hertz. And this is for string A. 440 hertz equals 1 over 2 times the length, which is 0.3 meters, times the square root of our tension, which is what we're solving for, divided by 0.005 kilograms per meter. So if we do this for both, we get that the tension in both strings is exactly 348.48 newtons. So with that, part B asks how many beats would occur between the third harmonic of the 0.3 meter string and the second harmonic of the 0.2 meter string. So the third harmonic is just the frequency of the first harmonic times 3, and the second harmonic is the first harmonic's frequency times 2. So the third harmonic of the 0.3 meter long string, that's for the note with 440 hertz. We multiply that frequency by 3, and we get 1,320 hertz. We multiply the frequency of the other string by 2, and that also gives us 1,320 hertz. And it asks for how many beats would occur between the third harmonic and the second harmonic of those two strings. And the frequency, the beat frequency, is equivalent to the exact value of the frequency of one string minus the frequency of the other string. And since they're both the same, it's obviously 0. So the number of beats that occur is 0. And then for part C, in an equal tempered scale, the notes would have frequencies given by 440 times 2 to the n over 12, with n equals 0 for A and n equals 7 for E. By what fraction does the tension have to change to tune the string to the equal tempered scale? And how many beats would occur between the third harmonic of the 0.3 meter string and the second harmonic of the 0.2 meter string for the equal tempered tuning? So we can plug these in. So 400 for the first string, n equals 0, second string, n equals 7. So we have our equation right here. We plug in 0 to this fraction up here equals 0, 2 to the 0 equals 1, 440 times 1 equals 440 hertz. And then for the other one, 440 times 2 to the 7 over 12 is 660 hertz. So again, the beat frequency is 0 hertz. So that answers that. And it asks for what fraction the tension has to change. But since these equal exactly what they were before, the tension doesn't have to change at all. So the answer is 0 or 1, however you want to answer that. And yeah, that is how you do problem number 3. I hope it was clear. And thank you for watching.